नहीं करता।
We can wait for a couple of more minutes, Madhukar.
So I think I'll start with like the last part of convolution that was left. So I will just clear that up, and if any of you have doubt about the assignment, then you can ask that, and Dan Madhukar will take over.
Okay. So you will be showing the assignment here.
I have sent the assignment already, so I think everybody must have seen it.
You meant you've uploaded, correct?
Yeah, I have uploaded and sent an announcement message.
You can ask them. Yes.
Yeah. Okay. So I think I shall start. Like it won't take too much of time. So screen is visible, right?
Yes.
Cool. Okay. So last time we were talking about this convolution, and maybe I didn't clarify some like part of it. So it's all about like how do you actually do the convolution when you're using this neural network. So I mean, just for revision, you remember. I hope you know that convolution is like this. So you have an image, and okay, just let me silence my phone. Yeah, so you have an image, and it's of some size. Let's say m by n. You start by taking you have a 3 by 3 kernel, or you can have 5 by 5 or other sizes, but mostly it's an odd number by odd number. And the reason is because when I'm calculating the convolution for, let's say, this pixel, then everything will be even about it. If the number of this size is odd, then this will be even. So there's one cell, one column before it, that one column like after it, and so on. So now when you start doing this, so you just place this kernel here. Okay, let me change the color. Okay, so you place the kernel here, and then you multiply the element. You do the element-wise multiplication. So you multiply this value with this one, this value with this one, and so on. And you take the sum and you replace this value in your final new output. You replace this value with this weighted sum. So the point is, if I denote these numbers by weights, then what I can do is this image is coming as an input. So remember in the initial part, in the traditional thing that we had, the normal neural network, we had a column as an input, and we used to take, like, if I have a layer here, then I will pass this thing to this neuron, this neuron, this neuron, and all the neurons will get each and every input. And this is what we're trying to avoid by using convolution. So instead of passing each input to all the neurons, we just say that the first neuron, this neuron, which is acting convolution, it will take all these values localized at 3 by 3 inputs. And I think I made a mistake last time that I said that all of them can have different weights. So no, what we do is, so this neuron, it's a special kind of neuron, and it has a specific, let's say, 9 weights. It has 9 weights, and what you do is you input this value to it, this value to it, this, and all the 9 values, and the weights are fixed. So there are 9 weights and all of them are fixed. And then you take the output of it, and that gives you the output for this thing. So for taking care of the boundary condition, you can either do like use the same value for all the other values. Like there are tricks to handle the boundary condition. I mean, but let's just assume that we are not worrying about the boundary for now, because if you place the matrix on the boundary, then you might have to, like if you try to place this matrix here, then it will go outside. So you can just, there are some convention of putting some values here by arbitrarily. So you can either swap it or duplicate these values and so on. But for now, we just notice this thing. So you take this cell, this 3 by 3 matrix, you multiply them and you get one output here. So you get this output. Then for getting the next output, you use the same weights and then you multiply these, all of these. You multiply this weight by the first weight, this value by the first weight, this value by the second, and so on. So the point is, it's like you have the matrix and you are sliding this kernel over it and calculating the weighted sum, and you are taking this, taking the average. Of course, you also, as Diganta, I think, pointed out, that you need to take the, you need to normalize it. So usually we just divide it by some number, like let's say n, to make sure that, okay, this value doesn't actually go out of bound. So assume this is 0 to 1, then we also want all the output to be 0 to 1. And if we are not getting that, we can always like clamp it if it is required. Anyway, so you just slide this kernel over this thing and you keep on calculating these values and you save them. And this is what they call as a feature map. And once you get the feature map, you perform one more operation, but we'll talk about it later. But for now, you just understand that there's a one neuron for each filter, and you need to learn all these weights, 9 weights. So when we form the convolution layer, we do not actually form just one filter. We create like 15, 13, 32, 512, or any number of filters, a large number of filters, and all of them are learned simultaneously, and they are applied to the image. So just for some explanation here. So if I have one image, the convolution layer will, let's say, learn 32 filters, and it will create 32 feature maps. All of them will contain some detail about some information about your input matrix. So it might have that this one will just capture the boundaries of your input, and this one will maybe capture something else, like, I don't know, maybe sharpen the image and all, and so on. So you learn multiple filters simultaneously, and each of this filter is determined by just one neuron, which will have weights and associated with like this value. All these 9 values are associated with this. So I'm assuming 3 by 3, it can have 5 by 5, 4 by 4, or anything, and you just keep on calculating. So this is up to this first part, which is convolution. So if there is any doubt till this point, then let me know. Remember that for each filter, there is another neuron. There is a new neuron, and we apply this convolution and get one feature map per neuron. And then these things are passed to the next layers for the processing, for the next layer processing. But there's one more step here, which is called as max pooling, which is very simple, and I'll explain it. So, but before that, if there's any doubt with this thing, then please let me know.
So there is exactly one neuron per filter.
Yeah, exactly. Yeah.
Okay. And so we're passing the entire image through each of those one neurons per filter.
Yeah, but in a very special way. So for example, I just copy these weights. It's not like it will output one thing. So for the first 3 by 3, it will output the first value. Then for the next, the slided thing, it will output the next value, and right, so on.
So we're like sliding the neuron over the image, sort of. I mean, we can implement it by copying, but yeah.
Yeah. I mean, we can implement it without, like, just imagine that you have this node and you are multiplying, like every input is coming and it is giving you multiple outputs. So it is giving you many outputs, and for each output, the inputs are this 3 by 3 patch, then the next patch, and so on. And the sliding is called by stride. If you remember that, it's called a stride. So you slide it by, let's say, 2 unit or 1 unit, and so on, and you get a new, usually a smaller matrix as output.
So each neuron is learning a 9 by 9 matrix of, like, basically what the filter is going to be.
Yeah, let's say k by k. So so each neuron here in the convolution layer will create one feature map for you, and you will get multiple feature maps. And usually if you try to see what it's learning, so it's very hazy. So I mean, for us as human, it's not even like at least I cannot understand what in what way, like what kind of feature map they're creating. So for us, we know that we do this like boundary or sharpening the image and so on. But what convolution layer does is like something which might not even make sense for us, but it somehow works. Okay, so now let's talk about this max pooling. So you'll see that the output of this thing.
So one thing, Hitat.
Yeah.
Yeah. So basically, you apply this thing once before you give these things as input, and then it works. Then it behaves like any other, like a DNN or something.
Uh, I didn't get your question. So this is a special layer which is called as like which we call as convolution layer. Okay.
Correct. And
And
there is only one such layer just before your, earlier you had your input layers, hidden layers, and your output layer.
yeah.
And now this is a layer before your input layer.
No, not before the input layer, because this is the input, right? This is the input. So it cannot be before the input layer.
Correct.
It is
So
after the
basically,
input
yeah,
layer.
what I meant is that, yeah, you pass the input to this layer, and what comes out of these layers becomes the standard input to the remaining part of the neural network.
Yeah, exactly. That is that. So it's basically feed forward. There is nothing like looping back like RNN. There's nothing like that. You just passed it, and then we apply something called as max pooling, which I'm explaining. And after that, following that, you can again apply the same, like another convolution layer, and then another convolution layer, and then you ultimately for the output, we usually what we do is then we do flattening. So after applying as many convolution layers we want, we do the flattening that will convert each feature map to a flat input, just as we wanted initially. And then we pass that to a, okay, then you pass that to your simple dense layer, the thing that we call a dense layer, which will receive all the outputs of this thing, and it will just, there will be an output layer, and then in whatever way you want to, let's say, I mean, you get the output and then you do what are the cost thing that you usually do. So it's like similar structure, but before this flattening of the thing, we apply this feature maps and max pooling in like, let's say multiple time, and then we do this flattening and after
So
that we do this.
so Hitat, so I guess to answer Madhukar's question, if it's only after flattening that it becomes the standard DNN. So
Yeah, the one we discussed. Yeah.
Yeah.
Yeah, exactly. After flattening, because as I mentioned in the first lecture, I said, I think that you have to flatten it as a column vector before applying it to a dense layer. So that is applied because remember, we do not do this flattening initially because this operation of convolution actually takes care of, needs this structure of the matrix. So it needs that, okay, I am sliding on 3x3 kernel over this or 4x4 kernel over this matrix. So it needs to have this structure. And usually it's not even just one matrix. So there are multiple channels like RGB or maybe something else, and then you apply those filters on each channel separately, and you get different feature maps, and then he performed the flattening. So I think it answers your question, right, Madhukar?
Correct. Yeah. So I'm worried about I mean, so from an analysis point of view, I'm worried about the structure. So as you said, so there is one layer which, which kind of reduces the dimension, along some dimension, something is reduced. And in a different one, you reduce some other dimension or something. So, right. So you're essentially reducing all these dimensions, right?
Yeah, so we reduce dimension in the max pooling part. Usually this one also reduces up because if my stride is, let's say 3, okay, and my 3x3 thing. So if my stride is of 3, then what will happen? I will reduce the size, okay, by because I'm traversing this matrix and I slide my kernel by 3 unit. So it will reduce the dimension, but usually the reduction happens in the max pooling part. So this is very important. Like we usually
so perhaps, after
you
explain the max pooling thing, it'll be clear.
Yeah. So max pooling is like very simple thing. So what you do is, let's get another color. Yeah. So you have this image, and we, after applying this convolution layer, we get some output. Let's say we are doing a max pooling on 2x2. So max pooling simply says that if I get a number 9 here, 10 here, 11 here, or 16 here, then I will write just one number, and that would be 16. Then I apply the same thing over the next. Let's say it's 4x4 for simplicity. And then I apply the same thing here. I take the next 2x2 without sliding. I take the next 2x2. And then I get the maximum number among these 4 quantities, and I write that number here. And similarly, I do for here and this part. And this is where the size dimension is reduced, so like significantly. So you just get, let's say, 8 and 9. And this is what max pooling is. So it's just like max and pooling. So you are just capturing the max out of it in a size 2 by 2. So you, in the TensorFlow, if you see the code, you'll see that there was a max pooling layer, I guess. And in the OCR notebook that I have sent, and it was 2 by 2, and you just take the maximum of that. So it's not the only way to do it. Of course, you can do some like cool stuff, like maybe take the average of these also and apply this, or apply some more complicated function. But usually, like if we say max pooling, then we just take the max number, and that will reduce the dimension. And after that, you start to, okay, sorry. Okay. After this, you do this part, you flatten it up, and then you pass it to your normal standard network that we studied so far. So that is it. So that's how you do the image, like the neural network which process image. So we have these things. And again, the most important like point of all this is that you are trying to use the local information instead of making it flat and forgetting all the, like we are not actually forgetting all the local information, but still for this network, it would be hard to understand that, let's say if I flatten it up, then this, so just imagine this, if I had this matrix and I flatten it up, then these numbers will be here and these number will be here. And it is hard to understand that the pixel here actually is related to the pixel here. Okay. So these pixels are related to each other, and that information is in some sense lost when we do the flattening directly. So instead of doing the flattening directly, we apply this convolution and then max pooling and maybe some iteration of these, and then finally we flatten it up and apply this normal thing that we do. So that is all for this part at least. Yeah. So if there's any question regarding this, then you can ask.
So the learning really happens after this, right? So this is
no. That is not true. So we also learned these weights. So this feature map, these filters are not actually like given to us. Like they are not like given to us beforehand, before that the neural network is given with these features, neurons. It's not like that. So you learn these weights as well. These 9 weights. That's 9 weights for this one, and so on. So we learn all of those.
Okay, sure.
Yeah. Okay, so I think yeah. So I think this is what I wanted to tell mostly. And other than that, I have this. We have this assignment. So I hope that all of you have seen this and also maybe read it. So if there's any doubt about it or anything, then of course you can contact me on email or maybe on phone call, or you can ask right now. If there's any general doubt, then ask right now that what this part is doing or whatever. So I'll be here for some time, like for taking your doubts, questions. I'm leaving here for a while. If somebody has not seen this, then they can maybe read it. So let's wait for 30 seconds, I guess, if it's okay, and see if anybody.
So while we wait, a couple of other questions, Hitarth. So
Yeah,
basically,
sure.
yeah. So basically, when we are trying to learn, so let's say, when we are learning this network, we are trying to learn these weights and biases. Correct. I mean, earlier when we were learning a network, we were trying to learn these weights and biases, right? So that's precisely what we are trying to learn.
Yeah.
Yeah, and those activation functions or whatever. Okay. Yeah. And yeah, so now when we are also trying to learn, these convolutional layers. So is there a standard set of things that we are learning? So are we learning, for instance, do we know that it's going to be a sliding thing? So are we learning the dimension of the window that we will be sliding?
No. So okay, so we fixed this with this kernel size. If I say 3 by 3, then it's fixed that okay, the kernel will be 3 by 3 size.
So
it
that's
learns
not
the
what
weights.
we are learning. That's fixed.
No, we are learning the weight. So for example, I showed you in the last I think let's say call it tutorial, that if you use this -1, -1, -1, -1, -1, 8, 1, -1, -1, -1, -1, -1. So that will detect your boundaries. And I told you like why it's obvious, because for each pixel, we are taking all of them and we are subtracting the summation of this from 8 times of this. So if this is 1 and all of them are also 1, then it means that this is not a boundary and it will become 0.
Certainly,
Right?
certainly,
So,
certainly.
So these weights, we are not telling the network that, okay, this is the feature map that you need to use. Of course, we can actually explicitly pass these weights, the kernel, that, okay, use this kernel as one of the feature map. That is also possible. But for now, we just tell it that, okay, 3 by 3 kernel, use 32 filters and find out the weights for by yourself. Just minimize the cost. That's all I want. And you just give the number of filters that you want to use, the size of the kernel, the size of the matrix that you want to use, and that's it. And it will perform everything else.
Correct. So cost with respect to what are you minimizing? What is the aim here?
Okay, so it's the same thing. So these are also neurons, right? So they have weights. So this kernel that I have, these values are what is acting like weights. Okay,
Correct.
because I mean, I think I didn't make it quite clear. So if I have an image, okay, I have an image, then I take the first, let's say 4 by 4 for now. I have to use 3 by 3 for now. You take 4 by 4, then you multiply this number with one weight. Let's call it W11. Then you multiply this with another number. Let's call it W12. Okay, and then you multiply this one with W33, right?
Correct.
And then you take after multiplication, you take the weighted, you take the sum. Like that's called, it's a weighted sum, and then you output one thing, and that would be the value of this pixel in the new matrix.
So what is the aim here? Correct. So what is the goal here? Should we output the smallest value, the biggest value? That's what I wanted to know.
No, not the smallest. You just in the first part, you are just calculating this output. You are just calculating the new matrix. I mean, you remember that buffalo picture that I showed last time. So you just apply this convolution and you get the boundaries. So that is the output of this one.
Correct, correct. I got it. So this is so the entire thing is being learned in one go. It's not that this is being learned separately and the other weights and biases are being learned separately.
No. Exactly this, all of this, like the theory will be similar. So
correct. I got it.
Okay,
certainly.
Yeah, just to explain on one point on this. So remember, this output is being calculated using these weights and also this output. So when you are calculating the rate of change of, if you remember this backpropagation thing that we did, we add another node. We say, let's call it W11, and then we calculate WC with respect to W11, right? And it was the sum of all the paths. So there are multiple paths now, because this output that we are getting, so this output is also dependent on this weight. This output is also dependent on this weight, and so you add them up to get the net derivative, the net partial derivative. So the idea is similar, the same thing. Just we have just localized the neurons and maybe change the way we use the neuron a little bit. That's it.
Yeah, certainly. Yeah, that helps. Thanks a lot.
So, Hitat, on these convolution nodes, the weights, it is similar. Although it is working on a kernel, just like other nodes, it does a linear transformation based on the weights, and then applies the same kind of activation function. Is an activation function also applied here, or that is done only after the flattening? So in that sense, is this node here a convolution node? I guess my question is two parts. One is, usually in the regular nodes, you apply the linear transformation expression. After that, you apply the activation. So does this convolution node also work similarly, or is the transformation function that is applied different in computing the feature as a function of the kernel on that 4x4 input?
So we do apply an activation function in this part. So because maybe ReLU or something, because we don't want negative values. Usually in the images, there's not much meaning in having negative values. So we do apply ReLU or some 10H or some other function, and then we get this output. So that's why I said there's just a neuron. So if it's a neuron, then there's activation function that's there. So it's similar to the other thing, but the only thing is that instead of having one output, this neuron can give you multiple outputs depending on which part or which, let's say, patch of this image or matrix it's reading. And on that basis, it will give you these outputs. So that's it. Okay, so I think there is no question for about this assignment. If there's none, then
Yeah, have you put the due date? Have you put the due date on it?
yeah, it's
Yes.
on Thursday,
If
September.
there are any questions from people after you have had a chance to review the assignment, please send an email or feel free to contact.
Yeah, so I think Madhukar can take like this up from here.
Yeah, Hitat, thanks. I'll present. So do you see my screen?
Yeah, it's visible.
Yeah, so yes, I'm going to talk about verified deep learning. So most of my slides here will be based on a book by, it's an ongoing book by Aus. Aus is a researcher in the field of formal methods, and he's been working on this book. And so most of my content will be based on this book, apart from a few examples that we will try to craft from here and there, so that we have something concrete while we are looking at things. We'll also look at a few papers that this is a fairly new field, and therefore the papers which are mostly recent, they are quite accessible in many cases. So we'll also look at a few papers to make these things clearer and more refined, the ideas more refined. Okay. So what I'll cover is going to be like this. So this is today's lecture is just an introduction of what it's going to be like. In the next week, I'll be covering the second and the third parts here, which is basically trying to represent them neural networks as graphs, and talking about correctness properties of them. And then we will learn how to, and then after looking at some amount of literature on the verification side, we'll come back to encoding of neural networks so that we can verify them. And we will look at some specialized solvers which can help us deal with the encodings that we have done. And many of these things, they do not work as it is. So there are some techniques that we have to apply. And we will look at one of them, which is called abstraction refinement. So this is what it is going to be like. This is still one part of the thing. So yeah, so before I proceed, you can for any doubt or any question or anything, you can write to me on this email address. I'll be sharing the slides, so this will be available. I'm also open to other means like WhatsApp, phone calls or something. So if you prefer that, you can tell me, you can send me an email, and then I'll share my phone number, and then we can talk on phone.
Yeah. One thing I want to add in your outline, if you can go to the previous.
Yeah, sorry.
Yeah, the 1 through 4, I guess Madhukar will be covering. In between, before you move to 5, there'll be some basics about SMT that I'll be covering, correct? So that is the...
Yeah, certainly. So this will be, so some of this will be interleaved by some SMT or constraint solving stuff that sir will cover, and then we will continue. So we'll try to present it in a way so that everything falls in place, and you can make sense of where we are going and why we are doing whatever we are doing. So we'll try to keep it that way. Okay, so this is, yeah, so of course, since we are talking about, we are talking about neural networks, and it's important to understand what neural networks are, and thanks to Hitarth we know what they are, how they behave, to a fairly good extent. Of course, this is not, I'm not trying to say that this is, I mean, there's a whole lot of literature that perhaps there is to look at, but this is certainly a good working introduction for us to proceed with the rest of the course. So we have known what these things are. We have known what neural networks are. We have known what, how they learn, what they learn and how they look. So now we want to analyze these objects, and this is what we are interested in. So the rest of the course will be, will in some sense talk about, some technique or something to analyze these objects. Okay, and there are two specific parts to the thing. So one part is that, while analyzing these things, what are the questions that we can ask? What is it that we can analyze? What properties can we talk about? What is it that we can prove? What is it that we can argue about? So this is one part of the thing. The other part of the thing is, how do we exactly do that? So how do we prove something? How do we argue something? How do we find a counterexample to something? And that's the logical part, the constraint solving part, which we will learn. So there are these two parts to the thing, and that's what sir was mentioning in the earlier slide, that we will interleave these things. So we'll learn about, what is it that we want to specify, what is it that we want to encode, what are the properties. And then, when we specify something, when we encode something, we'll try to make sense of it. When we'll specify a property, we'll try to prove the property, and therefore we will interleave it with some logical techniques to argue or to analyze. So this is how it's going to be. Yes, I'll motivate some of this a little bit. So this is a motivation that I derive from what are called airborne collision avoidance systems. So this is basically to avoid mid-air collisions between commercial aircrafts. And how it happens is, so if you can see this small image that I have here. So this own ship is the aircraft that we are talking about. We are worried about this aircraft, that it should not collide with something else. And you can see that there is this intruder aircraft which is coming from the right. And then there are a bunch of parameters or sensors, if you will. So there are things like the velocity or the speed of your own aircraft, the speed of the intruder aircraft. And then there are these angles along of the approach, and what angles do these things make. And the distance between the row, as you can see, is the distance between these two aircrafts. Okay, so this airborne collision avoidance system had to have a way to, so if you see some intruder coming from somewhere, and if the sensor senses some of these parameters, you wanted to know what to do. So you want to give some instruction to own ship, so that you can avoid a collision if possible. Okay, so this is what you want to do. So depending on the sensor inputs, you want to give you want to give an instruction to the own ship. And for that, what earlier how it used to work was that they had a lookup table. So basically, you have the values of all the sensors, and they had a lookup table to tell you, that if rho is this much, and the v own is this, and the v intruder is this, and the theta is this, and the psi is so much, then maybe you should turn right or turn left or keep moving, or turn sharp right or turn sharp left or something. So you have a bunch of instructions which are defined. They have a meaning. Okay, and you want to choose one of those instructions. So earlier this was happening through a lookup table, because you have to certainly you have to argue about so many different possibilities of the sensor inputs. And this was going to the size of 2 GB, and apparently it was not allowed to have so much memory to be able to certify these things before they can be used commercially. So this is, I'm just trying to motivate the use of DNN. So this was replaced, so this 2 GB table was replaced by DNNs, which took less than 3 MBs of memories. Okay, so you could learn this. You could have a neural network be trained on all these sensor inputs and the corresponding output. And you can now replace this whole lookup table by this DNN, which will tell you what to do. Given a bunch of inputs, it will have some output, and that's the output is what you want to do. Or if you have a bunch of outputs with some probabilities, and you want to do the one which has the maximum probability or the maximum weight. Okay, so this is what you want to do, which seems nice. It's also, in fact, it's also better than the earlier one, because now you have a DNN, so there is some continuity in place. Earlier, if your input sensors row did not match, then there is nothing that you can do. Here, you have a more continuous thing. So no matter what your input is, it will eventually compute some output. Okay, so this is continuous in nature, and this is better than the discrete lookup table. Okay, so we can get rid of the table, we can put the DNN in place, but before we do that, we have to guarantee something, right? So we have to give some behavioral guarantees. And the question that we are asking is that, what kind of behavioral guarantees can we give? Okay, and this is what we are. So what we'll learn in this course, in the remaining part of this course, we'll talk about this subject. Okay. Yeah. So at this point, it's important to understand that it's easier, when it is with programs, because programs have a notion of functional correctness. So suppose you're writing a program to sort an array of integers. So then you can mathematically prove that your program is correct, even if some of you have not done a course on formal verification, or or even if you're not aware of these topics or these subjects, you can still perhaps intuitively understand that since programs are mathematical objects, you can argue about them mathematically. Okay, and in fact you can do that. You can prove that a program written for let's say to sort a bunch of integers, or to find a minimum in an array of integers, or to compute a factorial, is always going to compute it correctly for a given input. You can argue that. You can mathematically derive this, prove this. Okay, so this part, this giving guarantee part is slightly easier when it comes to programs. By easier, I just mean that the specifying part of it is easier. Of course, the actually giving the guarantee is not really easy. It requires a lot of work. It's there are it's an undecidable problem. There are ways in which you can make this tractable, but that's a different problem in itself. But the point that I'm trying to make is that you can mathematically specify what you mean by correctness. This notion of functional correctness is missing in neural networks. Okay, and what do I mean by that? I mean to say that as compared to saying that a computer program will always compute factorial correctly, it's difficult to say that a neural network trained to classify an image of a cat as a cat will always do it correctly. What do you even mean by saying that? What do you even mean by saying that the neural network will always classify a cat, the image of a cat correctly? What does it mean? When do you say that it's certainly an image of a cat, and when do you say that it should classify this correctly? These things are not even clear, and it's not even it cannot be defined mathematically, which is what I'm trying to come to. And in fact, this is the reason why we are using deep learning to train these things, to learn when to classify an image of a cat as a cat, and when to not do so. Because if we knew a precise mathematical definition, we would have just simply coded it up as a program. That program would take any image as input, and then it will simply do the steps of the program and tell you precisely whether it is a cat or not. But these things cannot be defined properly, and that's why you are learning a network. So then what does it mean? Can we still ask some questions? Can we still give some answers? And that's what we are speaking about. Okay. So the question is that, okay, so you have these you have software, and now parts of the software is being replaced by neural networks. So what is it that we can speak about? So you have some software which has a deep learning component. You have software which earlier they did not have a deep learning component. And earlier you could talk about all these nice properties. Can you still talk about all these nice properties? And we will try to argue that yes, you can. And it'll be, in fact, it'll be good to talk about these properties. Okay, and what are the properties? The properties are safety, security, privacy. This is the kind of things that we argue about even in a non deep learning framework. robustness, which is one of the most talked about properties, consistency, and I'll come to each one of these. Safety, because as you saw, this is being I mean, this is being used in critical software system, avionics, robotics. So therefore, you want it to satisfy certain safety properties. Okay, and functional correctness, as we know, may not be fully expressible, but there can still be some desirable properties or some undesirable properties, and you may want to argue about those. For instance, you may want to say that if an intruder aircraft is approaching from the left, the network should never suggest the own ship to turn left. Okay, so you should not turn towards the direction of the intruder aircraft. Okay, we are talking about this. There are no levels here, so it's all happening in the same time. Okay, so if the intruder aircraft is approaching from the left, the network should never suggest to turn left. And this is a property, this is a define. Even if we don't know what the network is doing or what it should do, we should know that no matter what it does, it should at least do this. And this is the kind of stuff that we are going to talk about. Okay. Security, because of course, neural networks are everywhere and they are hackable. Yeah. Sorry, I didn't compile the latest code, it seems. Yeah, so I had another point in here which said that perhaps if you're so suppose your Alexa is a neural network based thing, and it's trying to learn, and one should not be able to hack into your Alexa and make it place an order wrongly on Amazon or something. So you don't want that to happen. So you have some security issues, and if you could specify those, as some desirable or undesirable properties, we can talk about them. Privacy, because neural net, because these networks can memorize the examples that they are trained on. Okay, and in fact there is an interesting paper on unintended memorization in neural networks, and there's a nice blog article at this link. You can read the blog article. If time permits, I'll try to cover this paper in as part of this course, or at least the motivation behind this paper as part of this course. And this is different from overfitting. We're not talking about learning or whatever, learning the training data really well so that you have 100% precision on the training. Overfitting is a problem that is generally present in case of, I mean, it's a problem. It's always there. It's a feature of the thing. If you keep training it too much, then you will overfit the training data. This memorization is in some sense it's a local problem. It could be about memorizing something for some network, for some model. Some network thought that some feature of some data is very important, and somehow it tried to give a lot of value, a lot of weight to that feature, while that feature might not have been important. Okay, and thus it can memorize that example. Okay, so this is something that's important. So we can talk about privacy. We can talk about robustness. Robustness is one of the most talked about things. So what happens if you have small changes in the input? Will it affect the output? So you had an image which was being classified as a cat. Now you change some pixels in there. Okay, it's still the image. It's still a cat. But there's some minor thing has changed. Some noise has come or something has come. Will you still identify it as a cat is an important question, and we want our networks to be robust, so we want small changes to not affect the output. I mean, at least when that's not desirable. Okay, so I mean it's true. Even we have these autonomous vehicles and so on, and they are detecting traffic lights, but these are real life conditions. The signboard may have some wear and tear. The lights may not be I mean, depending on the weather conditions, there may be less light, more light sometimes. There may be rain droplets, and you still want to, so you want your network to be robust to some extent, some properties at least. So maybe if we can define them properly, if we can say that if the brightness of an image which is being classified correctly is reduced by 10%, then it should still be classified correctly, if I have one such thing. Okay. So that kind of a thing. So if we have some, if you can specify some properties, then we can talk about them. We can try to see what, whether we can analyze them, whether we can prove them mathematically, whether we can argue about them logically. Consistency is another issue, and then it has to be, whatever your network predicts has to be consistent with the laws, and whether whether it is physics or nature or whatever, with your local laws there. Okay, so while predicting, let's say, if you have an image and you're trying to predict, who could be related in a child mother relationship, so the network must not predict two mothers for a child. That does not make sense, and therefore it's not. So it has to be consistent in some ways. For example, if you're predicting so this is something which is done quite a bit. You have a video and you pause the video at some point, and then you're trying to predict what happens in the next frame. Okay, and this is what happens in the next frame should perhaps, it should follow some laws of physics or some nature or something. It cannot be a random thing altogether. It has to be consistent with the video so far or something. Okay, so these are some properties that we have. So what we really have is a system which is our network, which has learned, and a bunch of properties, right? I mean, it could be a robustness property or a safety property or whatever, but it's a property that we can talk about. We can write it down, we can define it. Okay, so you have a system and a property, and this is not this is not an unknown setting. So software verification tells us what to do when we have a system and a property. It says that, look, you can write the property in the same language as you write the system in, and then and then you can perhaps make logical tools to argue about them. Okay, so this is something that we have learned from software verification, and a lot of techniques have been developed to do this kind of a thing. So given a system and a property, a lot of techniques have been developed to tell you whether the system satisfies the property or not. And this is, once again, we are asking the same question. Of course, the properties are going to be different. The system is different from what we have seen so far. But the point that we are trying to make is that, that really does not prevent us from talking about this once again. We can perhaps leverage the same techniques to argue about, some systems and some properties. We may not be able to do all that we have done in program verification. Of course, that's a mature field, and this is relatively new, much newer, in fact. You cannot perhaps do all, but is there, can we at least talk about it? Can we do something there? And the answer is indeed yes, and that's why we are going through this course, and we'll see what is it that we can do. Okay, so now, of course, we have seen neural networks, and Hitat has given a very clear picture of how they are, and how they learn and what they look like. And of course, we have seen, so we have seen them. So they're not very different from programs. If you think about it, of course, I mean, this is not how we write programs traditionally, but they are like programs, and no one can write a program like that. What are this? You have some input, you have some output, and there's some computation happening, which is what you have in programs. You have some input, you have some output, and then there is some computation happening. What is the computation? Is it could be different for traditional programs, and it could be a little different here with all these non-linear activation functions and weights and biases, but it's still a program. Okay, so the point that I'm trying to say is that to make is that it's indeed just a program. So I mean, of course, so we can take a look at the constraint-based verification that we do for programs. It's just that these programs are a little messy. Okay, and what do I mean by that? So consider an example here. Okay, this is a very simple example. Of course, this is not even messy. To be very truthful, but the point is that this is how it can look like, and you can understand that for simple network, if this is like that, then it can become really messy. Okay, so we'll take a look at this toy example here. So what do we have? So we have an input layer which is V11, and that's the input, and then there are there is this hidden layer with two neurons, V21 and V22. And then there is an output layer, which is V31. And then there are weights. Suppose the biases are nothing. Okay, so there is no bias. Okay. One thing that I wanted to remark here, I think, Hitat had mentioned that already, but So the biases don't add to the expressiveness of a neural network. What you can do with bias is something that you can do without bias by perhaps adding more neurons or something. So biases don't really make it more expressive. Okay, what you can do with weights plus biases is something that you can do with weights alone. Okay, so it's okay to remove biases from here. This is not less expressive by any means. Okay, if you have to convert this to a program and also to understand what this means, so as you can see on the right, you have this program which is this toy network here. Okay, which takes an input a real number which is v11. Okay, and it has other real numbers v21, 22, and 31. Okay, and what happens is something which is very simple. This is, it's not even something that we should worry about. So v21 is 1 times v11, which you can see from the edge with weight 1 that goes from 11 to 21. And the activation function at v21 and v22 is relu. Okay, so what this means is that, if v21 is less than equal to 0, then it should be set to 0. Otherwise it should be left as it is. Okay, so otherwise I don't fiddle with v21. But if it is less than equal to 0, it's made 0. Okay, similarly v22 is -1 into v11, and once again, if it is less than 0, we make it 0. Okay, v31 is nothing but the sum of 21 and 22, because both the edges have weight 1 and there's no activation function there. So you simply return v31, which is your output. Okay, and now the point is that we have this program, and we may have some properties that we want to talk about. Okay, so we may want to ask what happens. Is it always the case that the output is positive? Is it always the case that the output is same as the input? We can ask some questions, and we can ask those questions in the context of this program itself. So we can write this program into a logical formula, write the property also as a logical formula there, and we can verify this program. Okay, so verifying this network is exactly like verifying this program. Okay, and I've tried to encode this into SMT2 so that we can take a look at it. Wait, I'll share my browser. Is my browser visible or is it not?
No, it is not.
Correct. Yeah. So maybe I'll have to share it again. Wait.
Yeah, there's one point that I wanted to make here, Madhukar. If you could go back to the slide.
Yeah, certainly, sir.
See, that's kind of interesting. So you translated the thing into, if you can go back to the program.
Okay, just 1 second. Yeah. Can you see it?
Yeah. See, this when in this code, it is just a program that manipulates real numbers. It's implementing some function. Okay? Now, when you treat it that way, of course, you could prove some real, function properties. Okay, how much that will be? But this one is in this case, it was if this were a real neural network solving some problem, like you said, recognition of thing and so on. So the challenge that you mentioned earlier of what is it that what the specification is, it becomes more challenging when you want to express the property in terms of when you relate these real number outputs that it produces to certain features or decisions that you make. Okay, so that aspect is one thing. I'm trying to see what I'm trying to highlight the point. So there's no point in proving some real-time properties, okay, which may also have a bearing on the actual the outcome or output, the way that this thing is being used. Okay, so that may also be relevant, but I think the specification challenge that you mentioned becomes harder when some real number output based on that you have to proclaim that the output is a cat, okay, and that is one, okay, that is one challenge. The other is that I guess in the case of neural networks, the scale is also another challenge, correct? The number of nodes, etc.
Correct. Which is when it gets messy, which is exactly the point. Yes.
So those are the 2 points that I wanted to make. Yeah.
Correct. Certainly. Yeah. So of course the point about them being messy is certainly there, and one can see that this is of course this is less than a toy. I think this is a very silly example. There are it can get into several layers and several neurons per layer, many neurons per layer.
So in
And
this illustration, maybe you'll be proving some properties that are number theoretic, but for more realistic examples, those properties will have to be somewhat different, I guess, or at least relate these real numbers with the actual outcomes.
Correct. Yeah, certainly. Yeah. So so one small remark with respect to that. So earlier we were talking about this airborne collision avoidance system. So what you want to do is you want to give a bunch of instructions, and suppose your instructions are one of these 5, which says that you can keep moving, you can turn left, you can turn right, you can turn sharp left, or you can turn sharp right. Suppose one of these 5 is what you're, and therefore you have an output layer which consists of these 5 neurons. And depending on what output you calculate, you select the one which gets the maximum weight, or which gets the maximum value. And therefore, and now you can talk about more involved properties, not just number theoretic properties that V31 is positive and something is negative. You can actually talk about concrete properties that if the intruder aircraft is coming from the left, which is a sensor input, then the instruction is never to turn left. Okay, and you can try to argue that it will never be the case that if an intruder is coming from the left, the turn left or the turn sharp left can never be the maximum of the 5. So this is something that you can talk about. So you can talk about more involved properties as you progress, of course. So this once again, this is just a silly example, and we are just trying to show that look, verifying this in principle is similar to verifying the corresponding program. The neural network corresponds to a program, and verifying the property corresponds to verifying the property of the program. Whether we do this or not, and is this the best way to do it, is a separate question. But the point is that in principle, this is doable, and this is all that I'm trying to show here. Yeah. So I'll try to.
I have a question. So
Yeah.
We have the weights here for the network are sort of given. So are we basically working with networks that we have already trained and now want to verify the properties?
Correct. We are working with, so basically, you have trained a network to do something. Now how do you know that it will do it?
Right.
Okay. So that's the question that we are asking. So you've trained a network to do something, and you want to see how robust it is, or how does it satisfy some safety properties? Can you still give some guarantees about it? You may not be able to express entirely mathematically what this network is doing, but does that prevent you from posing a few questions about some of the desirable properties?
Yeah. So whoever asked that question, so what else did you have in mind? Certainly, most of the recent work in applying constraint solving and other traditional verification methods to this area, a significant part of it have been dealing with, are concerned with showing certain useful properties they are able to verify given the weights, okay, for an actual system now. And, what else did you have in mind? What else? Yeah.
So it's not like I had something very concrete, but I was thinking maybe we could verify properties of the training process itself.
Correct. Okay. So which is what I guess that you had, and actually Madhukar and I were discussing. So you could, but I wonder if these techniques. So there are 2 questions. Okay. Madhukar, we had when Hitarth was explaining this backward propagation. In theory, we thought that okay, that backward propagation is a synthesis problem, could be viewed as a synthesis problem of, does there exist some set of weights, okay, to make that cost function minimum, or that cost function minimum enough to answer certain questions correctly, okay? So if you did that, then maybe you could use these techniques to do that. But when I started thinking about it, the mathematics there is, with involving partial derivative, gradient descent, etc. Yeah, so that is almost like, either you could say verifying the correctness of a gradient descent back propagation algorithm, okay? Or if you want to, if you want to throw away the propagation algorithm, express it completely as a constraint solving problem, then it will be a synthesis problem, and a synthesis constraint solvers like SMT solvers have been used for a synthesis problem of that, not that kind, but of some things. Now the question is whether, when these BAP training methods are doing so well, I very much doubt if constraint solver, even if it can do, whether it is can do as well or not, because of the kind of the non-linearity involved in here, and constraint solvers work best, do not work best for non-linear functions, or in all the cases. But certainly that is a problem, but that is not what most people have applied so far to it, for the reasons that I just now pointed out.
I see. I mean, I wasn't thinking so much as to replace backpropagation, but to sort of limit the possibilities that backpropagation might have to throw.
I see. Okay, that's interesting. If some.
But yeah, I mean, I don't have any concrete thing in mind of how to do that. Or
This is somewhat similar to, I'm sorry, I'm taking some,
yeah, no. It's certainly, the discussion is certainly important.
Yeah, you see, there are these things. And when I tried to offer this course, or at least for the projects, we were thinking, for example, there are people who are applying machine learning techniques to for implementing certain heuristics in making decisions within an SMT solver and SAT solver.
I see.
Okay?
Yeah.
That work is is there. There is a community that does. There's one person called Kuldeep Neal at NUS, okay, who has made a name for himself by doing that, and he's been quite successful. Okay? He builds a new generation of SAT solvers where he has used machine learning techniques to do. I mean, we will be talking about some heuristics when I talk about the SAT solver, okay, later on. So there he's putting in a machine learning module inside a SAT solver, and that nobody, so far people have done it for SAT solver, but nobody has done it for SMT solvers. But that could be an interesting project as well. How well it works, etc., remains to be seen. So that's another direction in which these things can be applied. But no one has used a neural network there. Okay, they've used other kinds of machine learning things because they're a little bit uncertain about the efficiency. So efficiency is very important there for SAT solver and so on. Whether these neural networks will be as efficient, it is unclear. And was the concern that they expressed when I posed this question: if a neural network can be used. Okay, if someone is very interested in this course, to look into that, if they get so excited when I present the solvers, and if they want to pursue that for a project, assuming that we can define the topic, they are welcome to consider that. Okay, I would consider that. Yeah. Go ahead.
Yeah, certainly. Yeah, so a couple of things. I think just some points that I had. So one thing is that so of course I mean yeah. So for instance, in let's say, you're doing SAT solving and you want to, I don't know if you know the algo, and perhaps sir will cover this thing anyway. But there are some places where you find out which variable to branch on. You want to decide on some variable and you
That's
want
the
to
one that,
branch on.
yeah, yeah.
Yeah, so you may want to see which variable to branch on. You may want to do this through by learning, by training a neural network to find out which variable to branch on, and you want to use that network to tell you the variable, the next variable to branch on. So if you want to do something like that, then once again, the problem comes to arguing about some property of that neural network which you have trained for finding out the next the next variable to branch on. So then it becomes similar. In the other case, when we are talking about, so yeah, of course, as you said, you've not thought about it yourself very concretely, and even I have not thought about it very concretely. But when you're talking about the training part, remember that the training part is a normal program. It's not about, we are not talking about, so neural network is an artifact resulting from there. It's an artifact of a machine learning algo. The machine learning algo is like a normal program. So if you want to verify properties about that program, of course, because it's a machine learning program, it may have certain other challenges, but it still falls under program verification. I mean, by falling under program verification, I don't mean to differentiate between the two, but I'm saying that perhaps the traditional verification techniques can be applied more directly there. It's a machine learning algo, which is like a traditional program. It does not work on neural networks. Okay, and later you specify them. So you create these artifacts which are your trained neural networks. And when you create these artifacts, and if these artifacts are what you want to verify, what you want to specify properties about these artifacts, then it becomes a different thing. So of course there are these different questions, and we have to understand what it means to do this there, and to do it with a neural network, or to do it with a training algo. And yeah, and these may have different solutions or different ways to proceed, but they're all very interesting questions, certainly. And they all talk about having some algo or some artifact or some some machine learning uh, algorithm, and verifying properties about that, or having some some such neural network and verifying properties about that. So these are slightly different, but certainly are all related under this concept of verification.
I see.
Yeah, so I was telling you that this is something that we have I've tried to. So here is the program, and I will try to show you that you can specify this program into a logical language, in particular the SMT tool language used by Z3 solver, and then we'll employ the solver to do it for us. So I'll stop sharing the slides and start sharing my browser. Can you see the? Can you see my browser?
Yeah, it's visible.
Yeah. Okay. Okay. So what is it that we have? We have. So we have this network, right? So we had this toy example, right? And we are trying to verify a DNN, a property of for that toy example. And what is the property that we want to verify? We want to verify this property here, that if the input is non-negative, which is V11, if you remember, was the input. So if V11 is non-negative, then the output equals the input. Okay, this is what we want to verify, that if V11 is non-negative, then the output really equals the input. Okay, and this property is true for this network. Okay, so we can verify this, and in fact this is what we are trying to verify here. Okay, so I'm trying to specify this property here. So this is the precondition, that the input is non-negative. Okay, so I'm declaring these real variables. We have not given a Z3 tutorial yet, but many of you said that these things, and at least some of this will be clear. A lot of this will be clear even without a proper Z3 tutorial, which we'll come to a little later. Okay, yeah, but do stop me if any of this thing is not clear to you. Okay. Okay, so we have these four real variables. We are trying to assert this precondition which says that the input is non-negative. So this one, it's a prefix notation, as opposed to how we write infix when we.
I thought that there, did we go through a brief Z3 tutorial? Of course. I thought maybe I'm see, because I'm doing two courses. I know some of you who did who are also doing MCSV have already seen Z3, but did we not have a brief Z3 tutorial in this course? How many of you have never seen Z3?
Here we didn't have. They may have seen already. In fact,
I
some
think
of them.
we kind of postponed it, is it? So I thought that they saw, I went through some very simple examples. The examples, and we stopped at the thing. But in any case, so you might, yeah. So go ahead with whatever this thing that you have. So I have this question. So I forget if I went through it or not. So you're saying that I did not. So in which case then, I mean, you can go through it whatever level. So they'll have to use it anyway. So there'll be an assignment for them to use it on some neural network. So at some point, if there are people that have not seen it, want to have a tutorial, we can arrange for one. Okay. Go ahead.
Yeah, certainly. Yeah, so this one, so I'll still go ahead and explain this one, and you can certainly stop me if any of this syntax is not clear. Yeah, so we have defined 4 real variables here. We have asserted the precondition which says that the input is non-negative. Okay, so here you have v1 is greater than or equal to 0. Okay, to assert that the input is non-negative. And then, there is this hidden layer, which is what we have encoded here. So if you remember, v21 was getting an edge with weight 1 from v11, which means that, it'll exactly be v11 if it is positive. If v11 is not positive, it will be 0, which is what I have written in this if then else expression here, which says that, if this one says that if v11 is greater than 0, it will be v11. If it is not.
So here, a point that I want to make is when you declare a function v11 through v31, that means that that function can return any arbitrary real.
Okay, correct.
Yeah, that's right.
Correct. Yeah. So this one, yeah. So this is like saying that v11 is any arbitrary real number, and so are 21, 22, and 31. So we will not put any constraints because in the network, what is it that we had seen? So we'll in this code we will only have the constraints that were visible in the network, and then we want to know, is there any input for which, I mean, because if you see the property, it's like the property says that if the input is non-negative, then the output equals the input. So what we are really asking is that is there any input which is non-negative for which the output does not equal the input? Okay, and so therefore, we allow them to take these variables to take any values. They are free to take a value as long as it is not constrained by the network itself. So here is one constraint because of the precondition, which says that if the input is non-negative. Here are a few constraints because of the network. And what are the network specific constraints? So one network specific constraint is that the v21 should be v11 if it is bigger than 0, else it should be 0. Okay, so this is applying the weight of 1 along that edge, and then applying this ReLU activation function which Hitarth talked about. Okay, similarly v21, and this is once again a constraint from the network. So v22 is my if so normally what gets propagated along the edge with weight -1 is minus of v11, and now since the activation function at 22 is ReLU, if minus of v11 is bigger than 0, we continue with minus of v11. If it is not, then we propagate 0. Okay, so v22 is 0 otherwise. Okay, so these are the two constraints that we have from the hidden layer. The constraint of the output layer is very simple. It simply says that v31 is the sum of 21 and 22, and we are asserting the negation of the property, which is a way of asking, is there any input which satisfies all these conditions, the precondition as well as the network conditions, but does not satisfy the property. Okay, so is there any input for which 31 is not the same as 11? Okay, and then we can ask Z3 to tell us if this is satisfiable, and if we try, it says that it is not satisfiable. Okay, you can see this unsat coming here, which says that this is not satisfiable, which really means that, if the input is non-negative, the output really equals the input. Okay, I'll change this just a little bit to show you that, what happens when. Okay, so I've just changed this a little bit. Okay, so now I want to assert this property that the output always equals the input. Remember that earlier we had this property that, if the input is non-negative, then the output equals the input, which is actually the case. We verified that this was true. We got unsat here. Okay, so this property is not true. The output does not always equal the input. In fact, it equals the input. Certainly equals the input when the input is non-negative, but otherwise it may not equal the input. Okay. So this is same as the program as the SMT2 file from the last time, okay, except with one change that, there are no constraints on the input. Okay, so earlier you had one constraint on the input layer. For example, here you had one constraint on the input layer, that it was non-negative. Here you don't have any constraints on the input layer. The hidden layer certainly is as it is. The output layer is also as it is. And then we are trying to assert the same property, which is assert that 31 is not equal to 11, which is the negation of the property. And I have a get model thing here. So I want to find the counterexample. So I know that the property is not going to hold because I checked it earlier, of course. And if the property does not hold, you can always ask for a counterexample. So if you see this, it tells you that it is sat, which means that the property does not hold, and it gives you this counterexample. Okay, so this is not very difficult to see. So what does this counterexample say? It says that 22 is nothing but 1 by 2. Okay, and let's see what the input is. So the input is minus of 1 by 2. So the input is minus half, and if the input is minus half, you can do the calculation. You will notice that if you start with minus half as the input at V11, you will get the output as plus half, and therefore it is not going to be the same. Okay, so this is something that you can do. Okay, I am already exceeding the time, but in 2 minutes I'll tell you something. I'll give you one more.
Finish this thing up, Madhukar. So even if it takes 10 more minutes, okay. So there are some people that we need to do a little bit more extensive Z3 tutorial probably, but we will plan that. But that's all the more reason that you go through all of what you have. Yeah.
Correct. Yeah. Okay. So here is a third thing. Okay. So I have a different query here. Okay. So now I'm interested in finding if there exists an input in this range in 0,1 for which the output is in this range. Okay, so I'm interested in finding one such input. Okay, so I want to know if there is some input which belongs to the range 0,1 for which the corresponding output belongs to the range 0.5,1. Okay. And the point is that, of course, there exists one such input. In fact, many such inputs, right? Because, for every positive input, the output equals the input. We have verified this property earlier. Okay. So if you take 0.7 as the input, then you know that the input belongs to 0,1, and the output certainly is same as the input. So the output also belongs to 0.5,1 because it is 0.7. Okay. Now we want the solver to give us one such input. Okay, so this is exactly once again similar to the SMT2 file earlier. What you have in the hidden layer does not change because the network does not change. Similarly, the output layer does not change. Okay, what changes is constraints on the input and constraints on the output. Okay, so what is the input constraint? The input constraint says that V11, which is your input neuron, has to be between 0 and 1. Which I have expressed like this here, that it has to be bigger than equal to 0 and less than equal to 1. The only other change is the constraint on the output, which says that the 31, which is the output neuron, 31 should have the value which is bigger than or equal to 0.5 and less than or equal to 1. Okay, the rest of the network stays as it is. Once again, we know that this is SAT, so therefore check SAT should return SAT. And whenever it returns SAT, we are also interested in finding out a model. Okay, so now if we run this, it clearly says SAT, and it gives you know, the input 1/2 as a model. And of course, 1/2, you can verify that it is certainly 1/2 falls in this, and it certainly okay. If you want to get a different input, you can say that it has to be bigger than 0.7, and this will still be SAT. Okay, now you get 7/10, which is 0.7 as the input. Okay, if you remove this equality, you will get something different from 0.7. Okay, you get 1 as the input. Okay, so you can play with this. You can play with the queries. You can code up the network like this. The network is nothing but a big program with if then else's and some activation function. As long as you keep relu activation function, it's easier to code it up in this thing. If you use more complicated activation functions like sigmoid and stuff, then it becomes difficult because the non-linearity cannot be dealt with very easily by Z3. Okay, so if you have e to the power x and all, then Z3 may not be able to deal with it. But at least for relu, you can code these things up very nicely. You can write down your properties, you can verify the networks. Okay, so which tells us that yeah, I'll stop sharing this and I'll come back to the slide. Yeah, so which tells us that what we are trying to do is not something totally unthinkable. What we are trying to do is in fact something that we have been doing routinely. We have been trying to verify programs routinely, except that when we talk about neural networks, we may not want to do it like that because the programs will get messy, and perhaps this is not the way we should do it. Okay, so then we will try to learn what is it that we can do, how is it that we should do it, and then we will see it happening, and we'll have some project and we'll have some exercises where we will Diganta mentioned that what are we trying to do? Are we trying to train a thing or verify properties on a trained thing? So we may try to do an end-to-end exercise. Okay, so we may try to take a bunch of training data, train a network to do some task, and then try to verify whether the trained network can actually do that task or not by writing down some simple properties, trying to verify them. So this is what we are aiming to do here. Okay, so this was a brief introduction to it was an overview of what is going to happen. I will get to more details in the next week, where I'll talk about how do you represent neural networks as directly as acyclic graphs, which is again nothing new. We have already seen that in Hitarth's lectures, but we'll see it formally here, and we'll see that you can give it a structure, you can talk about its semantics, and then you can specify correctness properties using a specification language. And then later, you can encode the properties into a logical framework and try to argue about them. This is all that I have for today.
Okay, I have received a couple of queries about some people not having seen Z3 before. So we can plan a Z3.
Oh yeah. Okay, yeah, certainly.
Tutorial. Mainly, so in the model checking course, I concentrated more on the Boolean, part of it. We can do it with the, so by looking at the other decision procedures and so on. I mean, other, more SMT logic formulas like the way I introduced. So we can plan that other thing, but not, what I'm thinking is, I will schedule that on a special time slot outside of the class timing. Okay, is what I'm thinking right now, because some of you probably may want to skip it if you already known about it. But the emphasis will be on yes, covering the the features of Z3 specifically to show you on how it can do things outside of the Boolean domain. Okay, so that we will We will arrange. Okay.
Yeah,
Question
certainly.
for Hitarth
Yes.
about assignment.
Yeah, I'm here.
Question about assignment.
So there is no adjustment made in the code where we can store the values in the neurons, right? Like the feed forward function just returns the output in the last layer, but it does not store the values in the neurons in the hidden layer.
Yeah, so you need to implement that yourself in the
Okay.
SGD function. You can implement that. You just have to make a list and append that every time you multiply. That's it.
So we need some another self dot, say self dot neurons parameter, right? Variable, right?
It need not be self dot parameter because it will be a local parameter to that particular epoch. So if you are performing, or not even epoch, for a particular batch, so you're doing it for a batch and then you calculate this gradient for each example, and that thing that you need, that the gradient at each point or the values of each hidden neuron, that is required only for one backprop, right? So in the apply backprop on one example, in that function you will be using this. So it need not be a class attribute, at least instance attribute.
Can make it, right? I think it would be easier.
Yeah, you can make it. It doesn't make a difference, but yeah, I mean, I meant to say that it's a local variable. It's better to keep it a local, but it's your choice.
About SGD. So
Hmm.
in SGD, what we do is we choose a batch,
Hmm.
then we forward propagate for each example in the batch, back propagate, but do not update the weights, right? We update the weights only after all the examples in batch have been processed.
True. So you see there are two functions, applying backprop on a batch and apply backprop on example. So for a given batch, you will call that apply backprop on batch or on example, and for the whole batch, and then you sum them up and then you update the gradient, and then you proceed. And there's one thing maybe I didn't mention, that on each epoch, you will reshuffle the training data. Remember that on each epoch, you need to reshuffle it everything.
So
I think no.
we
I think
compute the gradients for each example, sum them up, and then subtract it.
Yeah, after multiplying with learning rate. Yeah.
Yeah. Okay. So how exactly this is faster than say not having batch at all?
Not having a batch, so you will, if you just increase the batch size to the whole training data size, and then see how long it takes, how long this takes, and you will understand how it's faster.
I could not
So
understand.
you are okay, I'm saying you are asking that how this
For every
taking this mini
example,
batches is
forward propagation and backward propagation, right?
yeah, but you are updating for mini batches, right? So you are more likely to reach your the bottom quickly. You will descend quickly in the initial part, and then maybe it will flatten up. So that's why I'm telling you that what you should do is that you should increase the batch size, the mini batch size, to, let's say, the size of the training data, and see how long it is taking. So you will realize at that point that it will take a very, very long time to get a bit of accuracy. If you are not applying SGD, it will take a long time. Like, you can actually experiment with that.
Perhaps his
Wait,
question.
I thought it was okay.
Experimental way of doing it.
Are we doing SGD or are we doing mini batch SGD? If we are doing mini batch SGD, then we take a mini batch. If we are doing a SGD, then we take only 1 point. So which one are we doing?
I think we're supposed to do batch only.
Okay, mini
Yeah,
batch.
you're supposed to use mini batches. Yeah.
And also, I thought using mini batches was faster as opposed to updating the weights on each example. I mean, on each data.
No. So we were comparing that initially the cost function was defined that you go through the whole training data and then you make an update. That is how I described
then
it initially.
Then the update is just one big step down, right? Because we are calculating the average of all the cost functions and then subtracting it by multiplying it with the learning rate.
Yeah, exactly. So what's your question again?
So I was thinking that it is faster as compared
to your voice is not hello.
Maybe he dropped out. Okay, so see, we are hitting 5 p.m. So let me make one logistic announcement here. People are welcome to stick around, okay, if they have questions, but you're not required to stick around the class.
Yeah, so if you have a class, then you can leave, definitely.
If Hitarth, if you're willing to take the questions and whoever want to clarify doubt, you're welcome to do so, okay?
Yeah,
those people can stick around to discuss the problem with Hitarth, and maybe you can show bring up the assignment today. So the rest, as I said, it is not a requirement that everyone should be there. Okay, so if they want to ask questions later on after the review, they are welcome to go, or if you choose to, you can stick around. Go ahead.
So what I thought was using mini batches to update the weights at the end of reading one batch. I mean, after reading each batch is faster as opposed to updating the weights after reading each individual data. Right.
No, not individual examples. So we are not even comparing. I mean, usually if you're not doing this, what they call as online training, you don't actually read one example and update your weights. You want to minimize the cost, not for one example, because remember, when you take this gradient descent algorithm and you apply it on something, you are decreasing the cost. If you apply it on one particular example, then you are only decreasing the cost for that example. So you are only guaranteed that, okay, your cost will decrease for this example, but it may not decrease for all the examples. So the idea was that if you really want to decrease the cost, like definitely you want to guarantee that it will decrease, then you need to compute this gradient over all the examples in the training data, okay? This was the initial idea that we have. Now SGD says that instead of calculating this gradient for the whole data, let's say 10,000 examples, we update on 10 examples on the mini batches of size 10. And then we do for the next 10, and then for the next 10, and so on. So this is faster because you are not waiting for calculating the gradient, the total